Okay, so let's do a quick recap because in this chapter we have done the exothermic, endothermic already, right? Okay, the one about energy in, energy out, and then we've also done rate of reaction, and then last week I taught you U. Okay, so let's just do a quick recap so that you know what I'm talking about. Okay, so rate of reaction is how fast something is. Okay? Wait, I need to close and open this account. Wait, Okay, wait, let me open it again. Hmm. Okay, now I can draw. Okay, so rate versus U. Okay, rate is the speed of the reaction. Okay, that means how fast it reacts. So rate is very straightforward. When the temperature is high, the rate of reaction is high. Why? The particles have more kinetic energy, they collide with each other more often, more particles achieve activation energy. Very straightforward. Okay? Pressure also, when the pressure is high, the rate of reaction is high. When the concentration is high, the rate of reaction is high. Why? Because the particles have more particles in the same volume. They're all close together, so they collide more often. Okay? Surface area, when the particle is powder, the surface area, the total surface area is very large. So the rate of reaction is high because more collisions. When there is a catalyst present, the rate of reaction is high because it lowers activation energy. Remember EA? Okay, EA is lowered when there is a catalyst. So this is rates. Okay, can remember how rate affects rate of reaction, how factors affect rate of reaction. Now yield, when the temperature is high, not automatically the yield is high. Yield is like this. X plus Y become XY. Yield means how much of the product is produced. So when there is more XY, there is more yield. Okay. So if it's high temperature and this forward reaction is endothermic, then yes, high temperature, high yield. If here the reactant has 2 moles, but here got 1 mole of gas, then yes, high pressure, high yield, because it goes to the side with
Wait, teacher.
less moles. Okay? Can?
Um, are you presenting your screen
Oh,
kernel?
I'm sorry. Yes, I'm sharing screen. Sorry. I closed the I closed the thing and I forgot to open it again. Okay, now I'm opening it again.
Okay.
Okay. Can see. Okay, did you miss anything that I was explaining?
Uh, I don't think so.
Okay. All right. Why is it so soft? I don't know why you're so soft. It's okay. Uh, okay. So when the concentration of the reactant is high, that means a lot of reactant. This one I add a lot, and then it will favor the forward. Okay. So last week we talked about all of these factors. Okay, we use reversible reaction in terms of temperature, pressure, concentration, and catalyst. Okay, can. All right. So today we're going to look at specific examples. So there are two specific examples we're going to look at. These are industrial processes. Do you know what I mean by industrial processes? That means it's done in the factory. Okay, so in the factory, right? In the factory, you want it very, very fast or very, very slow? Very, very fast lah. Where got factory says, I want you to make the bag as slow as possible. I want you to make the bicycle as slow as possible. Does it make sense, right? Okay. So these are industrial processes. There's two industrial processes. The first one is called Haber process, and the second one is called contact process. Haber process is to make ammonia. Okay? Okay. Why is it so important to make ammonia? Hmm. Okay. If this is the world population and this is time, what is the graph of the world population?
Going up.
Going up. Has it stopped going up? No. So we have how come last time I always ask my students this one, how come last time so few people and then suddenly people go up so fast? Last time, very easy to die. A woman can have 10 children. Only 2 children survive to adulthood because the children can die of diseases. The children can die of malnutrition. The children can die of the wife can die of childbirth. The woman can die of childbirth. Okay, so it's not so easy for people to survive. All right, they die very, very often. Okay, now number two, they die of diseases. There's no antibiotics, there is no medicine, there is no proper surgery. People didn't even know that you wash your hands to prevent bacterial infections. There is not enough food, food not so much. Okay, so what happens is because the population is so low, all people needed to do is they have their own garden, they have a few chickens, they have a few cows, they are enough to survive on the food that they grow. If not enough, the person on the other side grows wheat or grows corn or whatever, and then they can swap. And that's it. It doesn't need a lot to make them survive. Everybody plants food. Okay. But from the 19th century, world population started increasing. Why? Now there's antibiotics, there's better medicine, there is better, there's vaccines. Okay, so many things make people don't die. Okay, so in all these people that population explode, you need to feed them. You can have better machinery to plant crops. Crops means food that you plant. That's crops. Okay? Crops means food that you plant. So you can have better machinery to have better, dig it faster. But the most important thing is the soil must be fertile. You must have fertilizer. Now, 100 years ago, what do people use as fertilizer? Cow dung, lah. Cow dung, chicken dung, all of this, they used to use to fertilize the soil. But that is only enough to get crops once or twice a year. That's it. Okay, they can only get crops once or twice a year. But now, with the human population exploding, you need the soil to keep growing, 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 growing. The most important nutrients that the plants need are nitrogen, phosphorus, and potassium. The three, the one that they need in the most is nitrogen. Why? I'm sure you learned is bio. Carbohydrate is carbon, hydrogen, oxygen. You can make through photosynthesis. But protein is carbon, hydrogen, oxygen, nitrogen. Where am I supposed to get this nitrogen from? From the soil. I must get nitrogen from the soil. But if I have no fertilizer, where am I going to get the nitrogen from? So last time people just use natural fertilizer, but because the amount of human population is so large, you need a lot of fertilizer. So therefore, we need to make ammonia. The ammonia is then reacted with with acid to form fertilizer such as ammonium sulfate. Get it? This is fertilizer. Okay, can? So, Haber process was invented by this person named De Haber lah. Okay, now Haber did not invent ammonia. Haber invented a way to make ammonia very fast. Last time, they know about this equation, but nobody bothers to do it in the industry because it's too slow. That means, like this, I put the, I put the nitrogen and hydrogen in a closed system. I wait for 5 days. I only get 10% ammonia. Such a waste of time. Okay, so what happened is Mr. Haber decided to use different methods to get ammonia very, very fast and very, very high yield. Okay, so which comes the equation? Nitrogen, hydrogen. I put it together. I know this reaction is exothermic. Okay, all right. So what happens is you get the nitrogen from air. Okay, you get the hydrogen from methane. So the question will ask you, where do you get the hydrogen from? Where do you get the nitrogen from? The nitrogen is just from air because air is 78% nitrogen. The methane is natural gas. You know what's natural gas? You know
From
the
biomass.
petroleum, all that. It's natural gas. Okay? The one that you use in your gas cylinder, cooking gas at home. All right. Okay, can you write down this equation first? Scroll up. Okay, okay. Which one you want to write? Okay. Okay, yeah? All right. Okay. Joe, okay?
Yeah.
All right. Okay, so I'm gonna draw you. It's not exactly how it looks like, but this is what happens. Okay, so they get the nitrogen and they get the hydrogen and they pump it in, okay, and then they flow this into a place like this. Okay, so the first thing they need to do is they use iron beds. Why do they use iron beds? That means these beds got iron. Iron is a catalyst. And this catalyst is specifically for Haber process. The catalyst does not change the yield, but it makes the rate higher. It increases the rate. So I want the ammonia to be made very, very fast. I also want the ammonia to be made high yield. So the first thing I do is I put a catalyst. Okay? Can? Now the second thing I do is here we already know the forward reaction is exothermic. Okay, so if I use high temperature, the rate will be high, but the yield will be low. Correct not? Because forward is exo. All right. If I use low temperature, the rate would be low, but the yield will be high. Huh? How like that? So this is what I mean. If I do high temperature, I will get only 10% ammonia. But I get 10% ammonia every 15 minutes. High rate, but low yield. If I use very low temperature, I will get 50% ammonia. But I get 50% ammonia every 2 hours. Very high rate, but a very high yield, but very slow. So both of this, not very good. So what we do is Mr. Haber decided to compromise. He used 450 degrees Celsius here. 450 degrees Celsius is actually in industry is called a moderate temperature. So this gives me a rate that is high enough and a yield that is about 30%. If I go any higher, let's say I go to 600 degrees Celsius, the yield will only be 15% too low. So this gives me okay lah, 30% yield and an okay rate. So we compromise. He found this was the best choice. Okay? Now, okay, don't worry, I'll show it to you in a minute. Now, this one, right? How many moles of gas here at the reactant? 4 moles. Right? How many moles of gas in the product? 2 mole. So who has less? Product. So high pressure will favor who? Forward or reverse? High pressure favors the side with less moles. Remember that? Yeah. So what happens is if I use high pressure, it will get high yield. If I use high pressure, it will also give me high rate. So win-win. Okay. So the particular pressure that we use is specifically 200 atmosphere. If I want to use another unit, it's 20,000 kilopascal. You need to know both units. From here to here, just times 100. So this is the pressure. Because high pressure, high yield, high rate. Okay, so after I make this, I leave it here for about half an hour. After half an hour, I get a mixture of ammonia, nitrogen, and hydrogen, right? Okay, so I pour this into the next thing. And what I do is I cool it down. I make it very, very cold. When I make it very, very cold, what actually happens is that the ammonia becomes liquid because ammonia has a higher boiling point. So the ammonia will become liquid, but the nitrogen and hydrogen are still gas. Get it? So this gas, I can pump it and go back again. Do you understand? So I recycle the nitrogen and hydrogen. So the most important thing for you to remember for Haber process is catalyst, temperature, pressure. Okay? All right. Can you write this down? Oh, it's too small, sorry. Okay. Let's write this down. All right. So this is Haber process. Can remember? Can remember Haber process? So what do you need to know for this equation? You need, for this part, you need to know how to write the equation. You need to know where you get the nitrogen and hydrogen. And you need to know the conditions. Okay? Can? All right. Okay. So that is Haber. Wait, ah. Okay. Now we're going to talk about the next one, contact. Contact process is not by Mr. Contact. Contact process is just a name. It's to make sulfuric acid. Okay. Why is sulfuric acid important? Sulfuric acid is used to make a lot of things. Sulfuric acid is used to make car batteries. Sulfuric acid is used to make paint, dyes, plastic, chemicals, fertilizer. Basically, anything that we are sitting down, the plastic chair, we use sulfuric acid. That means it's one of the ingredients. The clothes we wear, it's probably has sulfuric acid in it, used as one of the ingredients. Plastic, anything uses sulfuric acid. So it's a very important reaction. Okay, so it is a four equation. There's four equations, but only one part of it needs catalyst. Okay, so the first equation is you take sulfur, which is a solid, you burn in oxygen, which is a gas, you get sulfur dioxide. Okay, this one nothing much. You just burn only. No need catalyst, no need nothing, and the equation is non-reversible, it's just one direction. Okay, so where do you get the sulfur from? We get the sulfur from sulfide ores. Okay, sulfide ore means like something like a zinc sulfide, it contains sulfur. So we can get the sulfur from there. Okay, now the second equation is the one that you need to remember. Okay, so this is the first part one. Okay, part two. Okay, this is the important one. Okay, because this one is sulfur dioxide gas react with oxygen. This reaction is reversible. Okay, this is sulfur dioxide gas react together with oxygen to produce sulfur trioxide gas. Okay, so obviously gas and then reversible. So what do I need? I need temperature, pressure, catalyst. The temperature is same like Haber, 450. So easy to remember. But the pressure is only 2 atmosphere or 200 kilopascal. Okay, why don't have higher pressure? Because at this pressure, the rate and the yield is already very high. No need to waste money, waste energy to put higher. Okay, so at this temperature, it's really very high. And then what happens is the catalyst I use is a bit special. It's called vanadium 5 oxide, V2O5. Okay, can you write this down? So this is step 2. Step 1, step 2. Huh? 4 steps only. Only this step I think you need, yeah. Only this step needs the special condition. Only step 2 needs the special condition. Can you write it down first? Then I can scroll down. Okay. 3. Okay. Step 3 is very easy. Step 3 is now I have the sulfur dioxide already. Okay. So actually, right, the sulfur dioxide can dissolve in water to become sulfuric acid. Sulfur trioxide can dissolve in water to form sulfuric acid. But we don't do this in the industry. The reason is because this reaction is very exothermic and the sulfuric acid and the sulfur trioxide won't dissolve. It will start coming out as vapor. Okay, and then with that, it cannot dissolve properly. Okay, so what we do is we instead of dissolving it straight in water, we split it apart. First, we take the sulfur trioxide, we dissolve in concentrated sulfuric acid. A lot of students are thinking, teacher, that's so stupid. You use sulfuric acid to make sulfuric acid. Yeah lah. It's like how you use yogurt to make more yogurt. You take a little bit of yogurt, put in milk, then you get more yogurt. Then after that, you sell that yogurt, but you keep a little bit and then you make more yogurt. Same concept. We take a little bit of sulfuric acid to make more sulfuric acid. So this sulfur trioxide is very, very, very soluble in the concentrated sulfuric acid, and it will become something called oleum. Oleum is basically super concentrated sulfuric acid. It's a very thick, like honey, like that, very, very thick. But what happens is when I take this oleum and dissolve in water, I will get a large quantity of concentrated sulfuric acid. No issues. This one cannot do direct because it's very exothermic. This one won't dissolve properly. It will bubble away and it's very dangerous. Okay, so the oleum is like a shortcut. I don't dissolve directly. I dissolve in one thing, then I put into another thing. Okay, can. Why you so late? What time did your class finish? What time did you read? Did you have co-curricular activity or something? Did you have any activity in school? Then why so late? Okay. Can you understand? Okay, Naman, later I'll give you time to write down everything. Okay. So, okay, so why do we use, okay, what in Haber, right, the pressure we use is 200 atmosphere, right? Okay. Why atmosphere is a unit for pressure? Why not higher? If it's higher, it's dangerous because too high pressure already. Okay, can in contact, the pressure we use is 2 atmosphere. Why don't we use higher? No need, because this 2 atmosphere already high yield and already high rate. Enough already, no need higher. And if it's higher some more, the higher it is, the more dangerous it is. Okay, same concept. Both reactions we do 450 degrees Celsius, right? Why not higher? It's dangerous and it's expensive. And also for Haber, the yield will decrease. Can you understand? Okay. All right. So congratulations. Safety, that means the higher pressure is dangerous. That's it. Economics is it's more expensive if you use higher pressure and higher temperature. That's it. Yeah, like what I explained just now. So summary, we did something called Haber process. Haber process is to make ammonia large quantities in the industry. Okay, so in order to make Haber, we use 450 degrees Celsius, 200 atmosphere, and we use iron as our catalyst. This is to make sure we get a very high yield and high rate of ammonia. Okay. The second process is contact process, is to make sulfuric acid. This is the 4 equations to make sulfuric acid. Okay, Ken, I will send these notes to your WhatsApp. Do you have your phone with you? It's there. Are you in the group? Yeah. Okay. Okay. I will send it. All right. Okay. This reaction is endothermic or exothermic? Exo. This is exothermic. How do you know it's exothermic? Because here it's negative. Okay. This industrial process is called Haber process. This is called enthalpy change. Okay, this is called enthalpy change. State the typical conditions and name the catalyst used in the industrial process. So I just told you, right? For Haber process, temperature is 450 degrees Celsius. Pressure is 200 atmosphere and the catalyst is iron. This one must memorize. This is fixed already. Uh, because this condition makes it fast and high yield. It's here. Mm. Okay. Come. Two methods of increasing the rate of reaction. So, adding a catalyst and, oh, sorry. Okay. Using iron powder. Okay, using iron powder because it causes large surface area. Right now. So this question is about rate. I want you to think about this one. I already give you one large surface area using iron powder. I want you to think. While you are thinking, I want you to do this one. Do you remember how to do this one? It's just calculate with okay, do this one. Do this one. Do this one while thinking about that. Come on, you can do it. Yeah, that's the easy one. Please increase temperature, increase pressure. Okay? Because the iron is already in powder, so cannot. Can you add this too, please, in the answer? Okay? This is to increase the rate. Okay, do the one below, the bond one. If you don't know how to do the bond question, we all sit down and cry because that's the easiest one. Okay? It's a good time to cry. Yeah. Joe, you've done already the question?
Yeah.
Okay. So listen carefully. Charge, listen carefully. Energy in minus energy out equals to enthalpy change. Okay? So in normal circumstances, they will give you this bond energy, how much? Then you times 1. And then this bond energy, how much? Then you times 3. And then this one, how much? Then you times 3. Then this one, how much? You times 3 like that. Get it? Okay.
Okay, yes. Okay.
Did you look through the notes or not?
Yeah.
Did you look through the video or not?
Yeah, but我看着你，
I don't know how you see.
啊，
It's impossible. All the videos are at least an hour long.
不是放在中语，放在中语。
Yeah, but that is inclusive of everything you're doing work in class. How can it be possible? No? If I find it, how? Okay, wait. Let's see. So in minus out equals to enthalpy change. Okay? Calculate the energy needed to break the bonds. So N3 is this one. How many of this do you have? 1. So you take 945 times 1 plus HH bond is this here. How many of this do you have? 1, 2, 3. So you take 435 times 3. Total is how much? Okay. 2250 is the total energy in. Okay. Now, what happens is usually they will give you another one, NH bond, and then they will tell you how much is it. And then they will ask you to count this one, 1, 2, 3, 4, 5, 6. Then you just take how much is this times 6, and that's your answer. But in this case, they ask the balik. What they do is they tell you in minus out already give you how much. So how much is each bond? Get it? So here in minus energy out equals to enthalpy change. In is 2250. Out, you don't know how much is what you're looking for. But the enthalpy change is how much? Negative 90. Your positive and negative must be very careful. Negative 90. So your enthalpy change is how much? Your energy out is how much? Energy out is basically energy release when bonds are formed. That's what we call energy out. Okay. So how much is the energy out? It's 2250 plus 90. So you get 2340. Okay. Now 2340 is how many NH bonds? 6. Okay, so NH bond is 2340 divided by 6. So you get 390.
这个 six 是那个
No, this one. Because they're finding one bond, how much? 1, 2, 3, 4, 5, 6. Get it?
Okay.
Okay?
Yeah.
Joe, you got it correct?
Yeah.
Okay, good. All right. Okay. An incomplete symbol preparation at ammonia laboratory. Okay, so what's missing? Water lah. Can see, right? You can see the equation. How many water? Just one water. Okay. This one you must see carefully. This is ammonium chloride, not ammonia chloride. Remember? Ammonium chloride. Because it's a 4, because the ion. NH3 is ammonia. NH4 is ammonium. Calculate the volume of ammonia formed, this ammonia formed, when 1.12 gram of calcium oxide is heated. Okay, what do you do first? You always find the amount of moles. Calcium oxide. Since they give you mass, you must use mass over molar mass. That's part 1, step 1. Step 2, find the amount of moles of ammonia because they're looking for the volume of ammonia. This one use ratio, okay? And step 3, you're supposed to find the volume of ammonia. I hope you know which one to do. Yes, it's given in the question. That is for aqueous solution. Volume over molar volume. Okay, ready? Okay. Calcium oxide mass over molar mass. Why? Because they give you mass. Molar mass, calcium is 40, oxygen is 16, so 56. You know that, ah? Please don't tell me you don't know. 0.02 mole. Part 2 is ratio. The ratio is 1 to 2. Can see that? 1 to 2. So 0.02 times 2, 0.04 mole. Okay? Volume of ammonia, you take amount of moles, multiply molar volume. Molar volume is 24, but that unit is in decimeter cube. This question give you centimeter cube, so you need to multiply. Okay, so you get 960. Can? Enjoy, you got it right? No.
Yeah, I got it right.
Can ah? Okay. Okay. Once you're done, okay, this question, wait, guys, wait. This question is homework. This one is homework. I don't want you to do now. This one is homework. Okay, the rest of this is homework. Okay, I want you to look at the second paper. Not this one. Wait, not this one. Okay, this one. This one first. This question. Uh, there's 4 documents. This one is part 3, Joe. Okay, this one is called part 3. This paper. The next page, basically.
Okay.
The next page of this. Okay? Okay, I want you all to do question 4 now. I want you all to do question 4. Just do question 4. The rest, don't worry about it. Just do question 4 first. Okay? Okay? So this one, remember rate and yield. Alright? Okay. Oxidation number. Okay, this one is next week. Next week we will learn about this. Okay. We finish the calculation, then we're done. Did you finish the calculation question? Yes? No? Did you finish the calculation? No? Okay. This one is homework also. Finishes as homework, okay? Can?
For me,
Yeah, D. The other paper we'll do next week. No need to finish it. Okay.